Hello, how are you? I hope all of you are fine. So we came for another lab. So this lab is lab 12 and the name of the lab is kinetic hydrolysis of ethyl acetate by conductivity method. We will try to find out the kinetic properties of a reaction with the help of the conductivity method. Okay. So you know what is the conductivity, because we already in the lab 7 we did the conductivity method. Also in the last lab or the lab before we also did the conductivity method. So that's how we know what is the conductivity. Okay, so with the help of that conductivity method we will find out the unknown concentration of the reaction. So we will explain that later. We will also find out the T half, that means the half lifetime of the T means time and half means half lifetime of a reaction. So as you know, the actually some of the reaction what we normally do in the lab, most of the reaction are very first reaction. Okay, so we cannot find out the speed of the reaction, that means the half-life of the reaction inside the lab, because it is so fast. So you need like much more modern technique to find out that. But some of the reaction, those are not that much fast, which can like finish it in like 1 hour. Okay, so that's why we have chosen this reaction, the ethyl acetate with the sodium hydroxide. So this reaction, it is not a very fast reaction and it is not a very slow reaction. Suppose rusting is a very slow reaction, and if you keep it for like few more days, then it will start rusting. So if you choose a rusting for an example, you will need like couple of days. So that's why we have chosen a reaction which will be finished in our lab time. Okay, so that's why we have chosen this. And what is the half lifetime? Half lifetime is that suppose with the help of the conductance, suppose at the beginning of the reaction the conductance is this. Okay, conductance is suppose 5000. Okay, and at the end of the reaction, when the reaction is ended, everything is reacted. So suppose at that time it is 2000, suppose. Okay, and it is 5000. And what is going to happen at the beginning, the reaction rate will be very fast, right? Why? Because of the concentration will remain high, so that all the reactant will be converted to the product, so there will be no change of the conductance. Okay, so suppose initial is 5000, the final is 2000. So what is the halfway point? That means the difference is 3000 and halfway will be 3500 around. Suppose it is this, or whatever it is this. Okay, so the time needed to go to that point, that means here it can be 5 minutes, 10 minutes, whatever, that is the half lifetime of the reaction. Okay, so with the help of these we will try to find out the half lifetime of the reaction. And what is the rate constant? We know that any rate is directly proportional to the concentration of the reactant, right? So these are the two reactant, and the power of the stoichiometry, like since these are the 1:1, so the power is 1:1. The acetate ion, sodium hydroxide ion and ethyl acetate, the concentration of the sodium hydroxide and concentration of the ethyl acetate. So it is a second order reaction. If it depends on if the reaction rate is depending on the concentration of the two reactant, then it's called a second order reaction. So what is the rate constant? This is rate, and rate constant is actually the proportional constant K. Okay, K of these one and this. Okay, so we are going to find out the K, rate constant. Okay, but the thing is that this is a second order reaction, but for our the calculation for the second order reaction is very hard. Even to do the experimental part, it's very complicated. So that's why we are going to convert the reaction to the first order reaction. How? So we can convert it to the first order reaction if we like give a very excess amount of one reactant. That means what we will do in our lab, we will add sodium hydroxide in very excess amount. Okay, so that the change of the concentration of this will be insignificant. Okay, so if the change of the concentration of one is insignificant, then it will be a first order reaction. Okay, so we will convert the second order reaction to the first order reaction for this. Okay, and we will also find out the activation energy. Okay, you know what is the activation energy? What is the activation energy? This is the minimum amount of energy what the reactant should have to convert to the product. Suppose normally the activation energy curve look like this. So this is called the activation energy. Okay, so all the reactants should go to above this curve to form the product. Okay, so with the increasing of the temperature, what will happen? The collision of the reactant will be increased. So much number of reactant will go to the convert to the product, but the activation energy will remain same. Okay, but the number of the product will be increased with the increasing of the temperature, with the increasing of the and with the change of the catalyst and some other factor, pressure. Okay, and for the rate constant, this K is also varies with the temperature. Okay, you will see that. So now come to the this is the I am explaining what we are going to find out from this lab. So ethyl acetate and sodium hydrolysis, this is called the basic hydrolysis. So there are some acidic hydrolysis, this is the basic hydrolysis. So what's going to happen? This is the ethyl acetate and sodium hydroxide. These two are going to form the sodium acetate and alcohol. Okay, so as you know, the conductivity, what forms the conductivity? What is responsible for the conductivity? The conductivity actually the ions are responsible for the conductivity, right? So among these two, which has the ions? Does it have any ions? No, it doesn't form any ions. Okay, so it will not give any conductance for this reaction. But sodium hydroxide, this is an ionic compound. It has the sodium ion as well as the hydroxide ion, right? So both of them are responsible for the conductance. Okay, and again this is also a ionic compound, the sodium acetate minus and plus. This will also take part in the conductance, but this will not take part in the conductance. Okay, so at any stage, if we try to find out the specific conductance of this reaction, then this will depends on the molar conductivity of sodium ion, the concentration of sodium ion, molar conductivity of hydroxide ion, the concentration of the hydroxide ion, and molar conductivity of the acetate ion. Okay, so sodium acetate also depends on the molar conductivity of acetate ion and concentration of the acetate ion. So sodium ion is actually same for there is no change for the sodium ion because this sodium will go here. So there is no change of the sodium ion. Okay, so we know what is the concentration, molar ion concentration. But what is the molar conductivity? This one actually basically depends on the concentration, depends on the size of the ions. How? Suppose for the hydroxide ion, okay, the number of hydroxide ion is here, and what will happen if you suppose you have a sodium hydroxide? As I said, we will add a lot of the sodium hydroxide ion. Okay, so we will add a lot of the sodium hydroxide ion. Why? To convert it to the first order reaction, because the first order reaction, the equation is very simple. The first order reaction equation is very simple. So we convert it to the first order reaction by using much more excess amount of the sodium hydroxide. Okay, so we have added this we normally add 20 ml of 0.5 molar sodium hydroxide. So here we will add very little amount of the acetate ion. Then what will happen? Acid ion. So ethyl acetate. So what will happen? This ethyl acetate will react with the sodium hydroxide and will form the sodium acetate and ethanol. Okay, a lot of the sodium hydroxide will remain unreacted. Okay, a very few amount of these will react with the sodium hydroxide. So this conductance, whatever the conductance at the beginning will be only for the sodium hydroxide, right? After the reaction, the conductance should be for the sodium hydroxide as well as for the ethyl acetate. But the problem is that molar conductivity, the molar conductivity depends, mostly depends on the size of the ions. The sodium ion and hydroxide ion, both are very small, right? But this hydroxide ion, when reacting with the sodium ethyl acetate, then it is forming the sodium acetate ion. This sodium acetate ion is very big, it cannot move. Okay, so it cannot move, so that's why the molar conductivity should be decreased. So that's why what is going to happen with the, when you are going to add the sodium ethyl acetate, then the conductivity is decreasing. Okay, so at the beginning it will decrease very sharply, but after 15 minutes around, okay, you will see that it is not going to decrease that much. Okay, then, and after sometimes there will be a plateau. Actually there is no change of the conductivity. Okay, so by using these techniques, we will try to use this technique to find out the unknown concentration, half-life time, rate constant, and activation energy. Okay, so determine the concentration of the unknown. It's very easy. So what we normally do, I will give you the data for this. Okay, you will get the data for this. I will give you data. There will be some blank and you have to fill it up, all those blanks. So first what we will do, we normally use at constant temperature. Since we are going to find out the unknown concentration, we will have to use the constant temperature. If we don't use the constant temperature, that can be changed. So that's why the first reaction we are going to use the temperature constant. So at the constant temperature, keep the temperature constant. At the constant temperature, we will take 1, 2, 3, 4, 5, 6 of the test tube. Okay, in 6 test tube we will actually put it in the calorimeter, having the temperature same. It may be 20 degrees Celsius temperature. Okay, so after keeping it for 10 minutes, then the temperature will be around 20 degree, will be around the temperature of the calorimeter. So then we will add 0.1 ml of acetate, ethyl acetate. In the first we will add, before adding we have to find out the conductance. So suppose before adding the conductance is 5000. I will give you in the data. Suppose for it is 5000. Then if you run it for long time, so, and we will keep stirring the solution. You have to keep stirring the solution and you have to take the reading continuously for at least 15 minutes. Okay, because why 15 minutes? If the half-life time is in between that's why you have to run it for the 15 minutes. Okay, so you got it 5000 and you also got the value here, all value you have here. And then after 15 minutes, taking the data for 15 minutes continuously, and during that time you definitely need to stir it. Okay, and you keep it. Okay, you don't have to bother about that, you have to keep it. And then after 1 hour you will take the data again. Suppose after 15 minutes the data is around 2300. Okay, after infinite time you see that the is around 2000. Okay, so this is the after infinite time, that means the reaction is done, completed. Okay, so the initial value should be 5000. I will give you this data in your, so suppose the initial value is 5000, the after t half you will get it. So after infinite time, if it is 2000. Okay, so the same way you are going to get the value for the 0.3 after finishing it. Then you have the another second test tube. Okay, second test tube. Then on the second test tube you are going to do the same thing, but this time you are going to add 0.5 ml. Okay, 0.3 ml. So 0.3 ml you are going to add, then you are going to get x naught and x infinity. So what will happen for the x infinity? So definitely that's this reaction, since the concentration of this is more, the amount of the ethyl acetate is more than the first one, so that's why this reaction will go a little down, isn't it? Okay, so the same way the 0.1, 0.2, this 0.9, it should go on this way. Okay, suppose this is for the 0.9. If it is 5000, this should be 5000 for all, but the end value at the infinite time, this value will go decrease with the increasing of the amount of the ethyl acetate. So suppose For the 0.9 it is 1000. Okay, so this is called the x naught and this is called the x infinity. Okay, so this value you are going to put x naught minus x infinity on the y axis and concentration on the x axis. Okay, so if you do that, then you are again going to put the unknown. Okay, we will give you the unknown, and what will you do? You will get same the x naught and x infinity value. Okay, and from that value, suppose if it comes here, you can get the y equal to mx plus c, and from there you can find out the concentration. It's very easy, right? So you can get the concentration of the unknown by using the conductivity method. Now the second part. So normally this lab needs to do like in one day we actually finish this part, because you have a lot of waiting time. So if you take the data for 15 minutes, 15 minutes, 15 minutes, 15 minutes, 15 minutes, 15 minutes. So here almost you need like 150 minutes around. Okay, although 7, but you have to do wash it, these a lot of times, so like 3 hours normally goes. So here another thing, that is the determination of rate constant. Okay, so what is the determination of the rate constant? K. As I said, what is K? K is only the proportional constant, rate constant. Okay, so how can you find out? So here what we did at the same temperature, but here the second thing, why we will do at the different temperature by changing the temperature, but this one will remain same, 0.5 ml. Here we change the amount of the ethyl acetate, but here we will keep the ethyl acetate same amount, but the temperature will be changed. Okay, so if we do that, the same thing is very easy. So with the increasing of the temperature, what will happen? The increasing of the temperature, the number of moles will get more, number of particles will get the activation energy. So the reaction will go much more towards the product, right? Reactant will go much more towards the product. So we will have 15 minutes data for 15 minutes, 20 minutes, 25 minutes, 30 minutes and 35 minutes. Okay, and we will take 0.5 ml. So for 20 minutes you will get it from here, and other things you have to do it. So normally what we do, we give you some like different batches having the temperature, okay, constant temperature. One maybe with the water bath with 15 degree, another one is 20 degree, 25 degree, 30 degree, 35 degree. Okay, so different water bath will be there, and you have to put your sample inside with the test tube. Okay, with the test tube we are going to put it, and then in all of those, suppose for the 15 degree, first you will take that test tube and you have to put the 0.5 ml. So at the initially you will check the conductance value, and you have to continuously measure the conductance for 15 minutes. Then after 15 minutes you will keep it, because you have to take it the value again after infinite time. So this is the infinite time, this is the T half. So here you have to find out the T half for this one. So how will you find out the T half? This is the 5000 and this is the 2000, as I said. So this is the 2000 and 3500 in the middle point. So from the 3500 you will extrapolate a line on the x-axis, and this is the time. This is the time. This is called the half-life time. So you are getting the half-life time. So there are two techniques to find out the activation energy. Rate constant K. So but if you know the half-life time of the reaction, it is very easy to find out the K. How? We know that T half is equal to 0.692 divided by K. Okay, so you know half-life time, you know 0.693, it's a constant value, so you can easily find out the K. How? K will go in this side, 0.693 divided by the time, like T half. Then you will easily get the T half of the reaction for the 15 degree. Okay, the same way you can get for the 20 degree, 25 degree, 30 degree, 35 degree. Okay, so you will get the T half and you will get the K. If you get the K and T half, you can easily get the ln K, ln K. Okay, so you get the ln K. So for here you see we are getting the actually rate constant for all the reactions. For all the reactions we are getting the rate constant. Okay, so we got the unknown concentration, we got T half, we got the rate constant. Now what? Now the activation energy we have to got. Okay, so how to get the activation energy? So according to the Arrhenius equation, the ln K is equal to E over RT multiplied with 1 over T plus ln Z. Okay, so you don't have to, this is the C, so you have to look at this one. So what is this? ln K you will get it from here. ln K value you will get it from here. So you are going to put all those ln K value in the y axis, and on the x axis you are going to put 1 over T value. Okay, so you have to convert this temperature into the Kelvin temperature. Okay, 1 over T. So Kelvin temperature, then if you put the ln K over 1 over T, then you will get a curve like this. So this curve is nothing but the minus E over R. Okay, it is not T. Minus E over R. Activation energy over R means, you know, this is the gas constants. So E over R. So here we know the value of R. Okay, whatever the slope you will get, we know the value of R. So you can easily find out the EA, activation energy, will be in the joule. You have to convert it to the kilojoule. Clear? So how, like all the calculation what will you do, and the experimental theory is done. I am going to show you. I already explained how to do the experimental part, but still I am going to show you. It's very simple. Hello, so this is the experimental part. I already discussed about the experimental part, but still, like, if you have any confusion, that's why. So in the experimental part it's very simple, but it has a lot of waiting time. So normally previously people, like, we were doing the lab in 2 days, but nowadays as I told to my students that at the beginning of the semester, that one lab has to stay on the lab for a long time. So this is the lab actually. So we expect to be there, to be in the lab for like more than 4 hours. Around 5 hours you need to be in the lab, only 1 day. Okay, so this is the lab. You are lucky that you don't have to stay here, stay in the lab. Okay, so for this lab experimental part, you need to have 9 big test tube on each group. Each group will have 9 test tube. Okay, so it has 2 parts. So first part is the 6 test tube you will use. Okay, 6 test tube. So first 6 test tube you will use for the first part. What will you do? Test tube number 1, 2, 3, 4, 5, 6. You will write it down on that way. So then we will have a water bath having the temperature 20 degrees Celsius. Try to look at this, 20 degrees Celsius. So you have a water bath with the 20 degrees Celsius temperature. So then what will happen? So you will put all of the test tube 1, 2, 3, 4, 5, 6 test tube inside the bath, and inside the water bath, and inside the water bath, and then you will keep it. You will have 20 ml of 0.5 molar. On each of them you have 20 ml of 0.5 molar sodium hydroxide. As I said, we are going to add excess amount of the sodium hydroxide, so the rate of the reaction becomes the first order reaction. Okay, so we are going to, so you will take that, and then you have to wait for the 10 minutes at least. Why this 10 minutes wait? So that the temperature inside the water, became the same. Okay, so if you wait for 10 minutes, then after 10 minutes the temperature inside the test tube, liquid inside the test tube will be same as the liquid outside the test tube. So these are the water is 20 degree, so the inside will be the 20 degree as well. So then first test tube, this is the first test tube, then you are going to add 0.1 molar is 1 ml of ethyl acetate. Okay, so if you are going to add 0.1 ml of ethyl acetate, then after adding, then so before adding, first of all you have to take the conductance. Okay, you know how to do the conductance. So you put the conductance and then measure the conductance, and after that, when the conductance will be stable, then you are going to add 0.1 ml of ethyl acetate, and after adding you have to stir it a little bit so that the reaction goes in process. So then after sometimes what will happen at the beginning, suppose the conductance is here, at the beginning conductance will decrease sharply, okay, as the concentration of the both reactants are very high, so it decreases sharply, then later on it will be like this, okay. So first what will you take the reading for 15 minutes continuously by stirring the mixture, then keep it and take the reading after 1 hour. So after 1 hour then you have to take the reading again, sorry, so it will plateau. So suppose this is an 1 hour, after 1 hour the reaction is done, okay, then you are going to take the reading again here, okay, x infinity, this is the x naught, this is x infinity. So same things you are going to do for the test tube number 2, test tube number 3, test tube number 4, test tube number 5. So for this 5, what you are going to do, you are going to add 0.1, 0.3, 0.5, 0.7 for the test tube number 4, 0.9 for the test tube number 5. But for the test tube number 6, we will give you the unknown, okay. So from the unknown, you will do the same thing, but you have to find out what is the concentration of the unknown, okay. Now take a look at this part 2. So this is the done with the part 1. In all cases you are going to take the reading after 1 hour also. First you have to take 15 minutes continuously, then you will keep it and you will start doing this, and after finishing the lab you will take the reading after of all of this, okay. So second part, in the second part you have taken 9 big test tube, you have 3 left, test tube number 7, 8 and 9, okay. So 20 ml of 0. Same thing, 20 ml of 0.5 mol of this. Here we did it the temperature, keeping the temperature constant. Here changing the temperature, but the amount of the ethyl acetate will remain constant. Clear? The amount of the ethyl acetate will remain constant. So then ethyl acetate, 0.5 ml of ethyl acetate we are going to add. Then you are going to add 0.5 ml of ethyl acetate to the test tube number 7. Okay. Then you are going to do again same thing like this. Take the reading for 15 minutes continuously and then keep it in the thermostat for 1 hour. So do the for the number 8 test tube, then you are going to add 20 ml of 0.5 mol of sodium hydroxide. This is 30 degrees Celsius. This is same for all. This is 9 test tube. This is for the 35 degrees Celsius, and this is same for all. Okay. So then if you do that, then you will get the all data for the table 1 and table 2. I'll give you the table 1 and table 2. You will do the lab report. Take care. Bye bye.